ionization energy. Ionization energy. It is represented as IE oblique I. Ionization energy, IE oblique I. Yesterday I given the definition. The amount of energy required to remove the electron from the outermost orbit of an isolated neutral gaseous atom. The amount of energy required to remove an electron from an isolated neutral gaseous atom is called as ionization energy. Okay, look at this. Let us consider A is an isolated neutral gaseous atom. A is an isolated neutral gaseous atom. And let us consider one electron in the outermost orbit. See, last orbit is called as outermost orbit. Let us take two orbits here, 1 and 2. Okay. Last orbit is outermost orbit. Between electron and nucleus, attraction forces are present. Okay. For example, let us consider this is nucleus, this pen is electron. Now electron is tightly held by the nucleus. Our nucleus is holding the electron tightly, right? So in order to remove this electron, we should apply some energy. Why? Because nucleus is holding the electron tightly. Clear? So that energy is called as ionization energy. The amount of energy required to remove the electron from the outermost orbit of an isolated neutral gaseous atom. Got it? The definition is very, very important. For example, look at this. M solid, we are removing electron. M gas, here also we are removing electron. In which case, the energy required to remove the electron is called as ionization energy. In which case? In second case. Why?
Gas.
In second case, metal is present in the gaseous state. In the first equation, metal is present in the solid state. So in this case only the energy required to remove the electron is called as ionization energy. Atom should be in the gaseous state. That is important condition. Okay, right. Yesterday I given one relation. Let us consider 4 electrons in the atom. 1, 2, 3, 4. First electron, second electron, third electron and the fourth electron. Amount of energy required to remove first electron is called as ionization energy 1, or also called as I1, simply called as I1. The amount of energy required to remove the second electron is called as ionization energy 2 or I2. Similarly, IE3 or also called I3. Ionization energy 4 or I4. Right? What is the relationship between these 4? Which is greater? I1 is less than, I2 is less than, I3 is less than, I4 and so on. So we can remove first electron easily. What is the meaning for this? I1 is less than I2 means you can remove first electron easily. Removal of second electron is little bit difficult. Third electron is highly difficult. Fourth electron is highly difficult. Right? What are the units of ionization energy? Energy, kilocalorie or kilojoules. Kilocalorie or kilojoules. Or even you can use electron volt also sometimes. Okay. Right. This is about the basic definition of ionization energy. Let us see the factors affecting ionization energy. Very, very important. Which factors affect the ionization energy? Factors affecting ionization energy. Factors affecting ionization energy. Let us discuss very important factors. Right. First one is radius. Radius or size. Radius are also called as size. Right. Second important factor, electronic configuration, because we use mostly these two factors, electronic configuration, and I'll give another factors also, but we do not discuss about them. Right. Guess what is another factor? What is another factor? Screening effect. Screening effect. Okay, screening effect are also called as shielding effect. Screening effect or shielding effect. Clear? But we will discuss about first two. First two are very important. Okay, first factor, radius. How radius affects the ionization energy? First factor, radius. I'll take one smaller atom and one larger atom, bigger atom. This is smaller atom. Let us consider it as A. This is bigger atom. Let us consider it as B. Bigger one and a smaller one. Right. In smaller atoms, electron is tightly held by the nucleus. Nuclear attraction force is present on the outermost electron, outermost orbit. Okay, so electron is tightly held by the nucleus in smaller atoms, because in smaller atoms, see the dash lines, dash, they are reaching the electron or not? Clear? But in larger atoms, nuclear charge do not acts on the outermost electron perfectly or completely, because of large distance. Nucleus power spreads up to certain distance only. Clear? So in the second atom, in the bigger atom, this electron is not affected by the nucleus. Okay, it is considered like a free electron. There is no force on it. For example, like this. See, loosely bonded electron, loosely held electron. So we can remove this electron easily. Loosely held. But in this case, electron is tightly held by the nucleus. We cannot remove. So simple logic. In smaller atoms, nuclear attraction power is present on the outermost electron or outermost orbit. In the bigger atoms, nuclear attraction power is not present on the outermost orbit or bigger atom. Now you tell me, in which case we can remove the electron easily? In case of B. Let us consider ionization energy as IE1 in this case actually. Or general relation I will give you, because you may get confusion. I am considering this as a ionization. Okay, consider that only. IE2, because generally what I given IE1 is less than IE2, so follow that one. Generalization. In this case, ionization energy 1 is less than ionization energy 2. Why? Because here nuclear attraction is more on the outermost electron. Clear? So what is the relation here? Ionization energy 1 is less than ionization energy 2. Got it? Ionization energy of atom B is less than ionization energy of atom A. Clear? Size and ionization energy. If size is less, ionization energy is more. If size is more, ionization energy is less. Clear? So that is the relation. So ionization energy is inversely proportional to size or radius. Let us take one example. First year group elements. Okay. First year group. Lithium, sodium, potassium, rubidium, cesium. Whose size is more here? Whose size is more? Cesium size is more. This is bigger atom. Bigger one. So has low ionization energy. Bigger atom, so low ionization energy. Lithium is smaller atom. Possess high ionization energy. right? What is the ionization energy order for the first A group elements? Ionization energy order. Lithium is greater or smaller? Lithium is greater than sodium, potassium, rubidium and cesium. Cesium has a low ionization energy because of its large radius. Right? Okay. Next, I'll explain about electronic configuration before going to discuss the ionization energy related to the size, left to right. Okay. First of all, let us complete electronic configurations and ionization energies. Okay. Right. Next factor, ionization energy. Electronic configuration. How electronic configuration affects ionization energy? Electronic configuration. Electronic configurations. One simple straightforward definition or sentence: the elements with the stable configurations. Elements are ions with the stable configurations possess a high ionization energy. What are stable configurations? See, for d orbital, d10 is stable, d5 is stable, completely filled, completely half filled. For p orbital, p6, p3. For some cases we consider s2 also completely filled, rare cases, right? Generally we consider p and d completely half filled, completely fully filled. In some cases we take s2 also as completely filled configuration, right? These are said to be stable configurations. Right? See, ionization energy depends on EC. EC stands for electronic configuration. These are stable configurations, right? So these configurations possess high ionization energy. Here only I am giving high ionization energy. Right? Elements with D10, D5, elements with P6, P3 are said to be stable configurations. Okay? Right? Let us see some examples. Nitrogen electronic configuration is 1s2, 2s2, 2p3. Nitrogen atomic number is 7. P3. Oxygen 1s2, 2s2, 2p4. Which is completely half filled? Nitrogen. P3. Stable configuration. Okay. So nitrogen ionization energy is greater than oxygen ionization energy. Okay. Next another example. Helium and lithium plus. What is its configuration? This is one different case. Okay. Helium 1s2, lithium 1s2. Lithium atomic number is remove one electron, 1s2. Both are having same configurations, right? How can we predict the ionization energy? If electronic configurations are same, then what we will consider? We will consider size. Whose size is smaller? The atom with a positive charge is smaller atom. Okay, this is smaller. So lithium plus ionization energy is greater than helium ionization energy. Here electronic configurations are same, but whose size is smaller? Lithium plus size, because cation size is smaller. If size is small, we know ionization energy is more, right? Electronic configuration concept, no doubt. Let us start one very, very important example. What happens to the ionization energy while we move from left to right in the periodic table? This is very, very important example. Let us see this. ionization energy variation, ionization energy variation in periods, ionization energy variation in periods, left to right in the periodic table. What happens to the size as we move from left to right? As we move from left to right means see this is periodic table. If we move from left to right, S block to P block, left to right, size decreases, and ionization energy increases, right? If size is small, what about ionization energy? Ionization energy is more. Size decreases, ionization energy increases. Let us take one important example: lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. See, we are moving towards right. If we move towards right, what happens to the size? Size decreases. If size decreases, then what happens to the ionization energy? Ionization energy should increase. So which symbol we have to keep here? Less than symbol or greater than symbol? Which symbol we have to keep? Lithium is having low ionization energy than beryllium. Correct. In general trend this is right, but we have exceptionals, right? Where we can see the exception case? Online students, can you tell me where we can see the exception? Nitrogen, oxygen, and in this place we can see the exceptional behavior. Why? Look at this. Because of stable electronic configurations. Very important. You have to prepare this. Okay. Beryllium is having completely filled configuration. What is beryllium configuration? 1s2, 2s2, completely filled. Here nitrogen is having completely half filled. 1s2, 2s2, 2p3. Very important. Okay. This ionization energy order, especially for these elements, right? Okay. Generally or frequently we will get four elements ionization energy comparison. I'll give you that 4 elements. Question: among the following, like carbon, nitrogen, oxygen, fluorine, which is having more ionization energy, or arrange the following elements in the increasing order of their ionization energy, right? Follow this one. First, which is having low ionization energy? Carbon after oxygen. See here, nitrogen is greater than oxygen, means oxygen is less than nitrogen only. No? Nitrogen is greater than oxygen means oxygen is less than nitrogen. Carbon is less than oxygen is less than nitrogen is less than fluorine. Very important. Frequently we will get these 4 elements or atoms. Okay. This is explained based on this generalized explanation. Clear? Online students, are you following, all of you? Are you getting, all of you? This is first ionization energy. This order is first ionization energy order. This is first ionization energy order. Very important. Let us compare the second ionization energy orders. Okay, before going to start second ionization energy orders, I will explain one general concept to you. I am taking sodium, and I am taking magnesium. Before going to start that example, let us have one example. Okay, on the electronic configuration, stable configurations. Sodium electronic configuration is 1s2, 2s2, 2p6 and 3s1. 1s2, 2p6 3s2. Is it stable configuration? No. Right. Remove one electron from this ionization energy IE1. What is IE1? Amount of energy required to remove first electron. So remove first electron. Sodium will convert it to sodium plus. Now what is its configuration? 1s2, 2s2, 2p6. This is the configuration of neon. If any element gets inert gas element configuration after removal of electron, it will get a high ionization energy. Remember, after removing one electron or two electrons or three electrons from any atom, if it gets inert gas element configuration, 1s2, 2s2, 2p6 is the neon configuration, then its ionization energy suddenly increases. Right? Okay. In order to remove next electron, you should apply more amount of energy. For example, if ionization energy is 100, ionization energy is 8000. See the difference, drastic or abrupt increase is taking place in the ionization energy. Generally, second ionization energy will be higher only. If this is 100, this is 200 in generally. If this is 200, this is 400. Just 100 increase will take place generally. But why sudden jump? Unexpected hike in the ionization energy is taking place here. After removing one electron, sodium is getting stable neon inert gas configuration. And removal of electrons from the inert gas element configuration is highly difficult. You should apply more amount of energy. Got it? After removing one electron, if you get any inert gas element configuration, removal of next electron is highly tough or difficulty. Remember this point. Let us consider the magnesium. Magnesium 1s2, 2s2, 2p6, 3s2. Okay. Ionization energy 1. Remove one electron. Magnesium plus. 1s2, 2s2, 2p6, 3s1. Is it inert gas configuration? No. Right? It is not inert gas element configuration. Right. Remember that point. Again, I am removing another electron. Minus electron. Then I will get a Mg plus 2. 1s2, 2s2, 2p6. This is neon configuration. Right. Now you tell me, after removing how many electrons magnesium is getting neon configuration? Excuse me. How many electrons? After removing 2 electrons, magnesium is getting inert gas element configuration. See, in generally, second ionization energy will be higher only, no doubt. 100, 200, 300 like that. So what is the expected ionization energy 3? General increase 100, 200, 300, 400 like that. But look at this. 7000. Why sudden jump in the ionization energy is taking place? Why? After removing 2 electrons, it is getting stable configuration. So instead of regular increase, abrupt increase takes place. Right? For sodium, in which ionization energy sudden jump in the ionization energy is taking place? In which ionization energy sudden jump? Second ionization energy. For magnesium, which ionization energy is very high? Third. Based on this point, we can give one statement. If any atom contains one valence electron, its second ionization energy is very high. See, sodium valence electrons. How many electrons are present in sodium? 1. So for sodium, second ionization energy is very high. Observe magnesium. In magnesium, valence electron means take last orbit 3, third orbit. How many valence electrons are present? So its third ionization energy is very high. Increase one. If one valence electron is present, second ionization energy is very high. If two valence electrons are present, third ionization energy is very high. Got it? Increase 1 plus 1. Number of valence electrons plus 1. For example, you can answer easily. For aluminum, which ionization energy is very, very high? 1s2, 2s2, 2p6, 3s2, 3p1. How many valence electrons are present here? How many valence electrons? These two are considered as valence. Valence means third. Third orbit is complete valence orbit. Third energy level. First, second. Second means 2s2p. Last valence 3s3p. So take 3 electrons. 1s, 2s2p. Second, 3s3p. In third, 3s and 3p are present. So how many valence electrons are present here? 3. So which ionization energy is very high? Fourth ionization energy is very high. Sudden jump takes place in its fourth ionization energy. Clear? Got it? Once look at this. The elements with the one valence electrons can be represented in the general format mx. Sodium chloride. For elements with two valence electrons are generally represented as mx2 type. How many valence electrons are present here? 3. So mx3. Very, very important model question. The compound having its second ionization energy is very high. Identify the formula of that compound. Identify the formula of that compound. The compound whose second ionization energy is very high. Identify the formula of that compound. Second ionization energy. See, mx1 type. Second ionization energy. The compound whose third ionization energy. Third ionization energy is very high. Identify the formula of that compound. mx2. The element whose fourth ionization energy is very high. Identify the formula of that compound. mx3. Clear? Here only I covered one model question. Right? Online students, are you getting or not? See one model question. 79.9, 120.2, 7925 kilocalories are successive ionization energy values of an element M. Identify the compound formed by that element or by the element. First option, MBr2, MBr3. Answer is second, MBr2. See here, very simple trick. Observe 79, 120 general increase only. There is no much gap, right? But 127,925 means very abrupt increase. So this is I1, I2, I3. Third ionization energy is very high. Third ionization energy is very high. If third ionization energy is very high, the compound formula is Mx2. See here, third ionization energy is very high. Correct or no? So Mx2 type compound means MbR2. Remember this. Prepare by heart this. Clear? Right. Questions will come based on these three only. Okay? Right. Completed. Next one, important note. Among all the elements in the periodic table, which element is having high ionization energy, or which group elements are having high ionization energy values? Inert gas elements are having high ionization energy values, right? Let us write that point. Inert gas elements possess high ionization energy values. What are inert gases? Helium, neon, argon, krypton, xenon, and radon. In generally, inert gas elements possess high ionization energy values because of octet configuration. Now, out of these, which is having high ionization energy? Comparison in between inert gases. Helium size is small, so helium is having high ionization energy. In generally, inert gases are having high ionization energy when compared with the other elements in the periodic table. If we compare inert gases, means comparison, internal comparison, which is having more ionization energy? Helium greater than, neon greater than, so on, xenon. Why helium is having high ionization energy? Because of its small size, high ionization energy. Okay, clear? Right. Next, electron affinity. Ionization energy means the amount of energy required to remove the electron. Ionization energy is opposite. The amount of energy released when an electron is added to isolated neutral gaseous atom. Reverse. In generally, see, let us take these two objects. Join these two objects. Some energy is coming out or not? Join these two. Energy, sound energy. Energy means sound energy. Sound is coming or not? Let us consider this is atom. This is an atom. This is electron. Atom and electron. Energy is coming out. Okay. Amount of energy released when an electron is added to outermost orbit. If we add electron to the atom, then energy will release out, right? Means atom is losing energy. Let us assume inside atom energy is present. When you add electron, that atom is releasing that energy. Means with respect to atom, that is negative or positive? Negative only. It is losing the energy. Atom is losing the energy. So electron affinity values in generally represented with a negative sign. Because atom is losing its energy. When you add the electron, atom will lose the energy. So electron affinity value is an exothermic process. Electron affinity process is an exothermic process. Because atom is losing the energy, releasing the energy. Exothermic process in generally. And it is negative sign. Delta H value is negative. Enthalpy, heat of reaction, enthalpy of reaction, delta H is negative sign because atom is losing the energy, right? the energy released when an electron is added to, tell me, outermost orbit of an isolated neutral gaseous atom is called as electron affinity. Look at this, one of you. This is one electron, this is atom, and this is outermost orbit. Second orbit is outermost orbit. You are adding electron. When you add electron, energy is released out. That released energy is called as electron affinity, and it is negative in general. So for electron affinity, we use this symbol. Delta H is negative according to thermodynamics. For exothermic reactions, delta H is negative. Electron affinity is a which process? Exothermic process. Energy is released. During addition of electron, energy is released. That's why delta H is negative. In thermodynamics, we have these signs. Delta H is negative, delta H positive. Clear? Right. Now you tell me. When we add electron, then only energy is released. That released energy is called as electron affinity. If we add electron easily, then more amount of energy is released out. More negative. If we are unable to add the electron, then energy will not release. Clear? If we are unable to add the electron, then energy will not release. Okay? Right. For which atom we can add electron easily? Smaller atom or larger atom? For which atom we can add electron easily? Okay, just a second. Remove this. A is smaller atom. B is bigger atom. Bigger. Let us consider one electron is going in this way. Just assume we have two atoms, one smaller atom and one bigger atom. Electron is going in this direction. It will be attracted by which atom easily? Smaller atom. Because in smaller atoms, positive charge is present on the outermost orbit. Positive charge. Nuclear attraction spreads up to outermost orbit. Anywhere you can get positive charge. Positive. So electron will be easily added because positive charge is there. Electron is negative. So for smaller atoms, you can add electron easily. For larger atoms, you cannot add electron easily. So for smaller atoms, electron affinity value is more negative. If more is the negative, more will be the electron affinity. Smaller atoms electron affinity will be more. Smaller atoms electron affinity value will be more. Larger atoms electron affinity will be lesser. More electron affinity values, less electron affinity values, because you cannot add electron easily to bigger atom. Why? Is there any positive charge on the outermost orbit? How can you add? If positive and negative is present, then you can add easily. In the larger atoms, positive charge do not present on the outermost orbit. Clear? I will give you one important exceptional case. You remember this order, general concept. For smaller atoms, electron affinity will be more or lesser? More. For bigger atoms, electron affinity? Yes. Clear? I will give you directly two important exceptional cases. Came several times in the objective exams, NEET, JEE Mains. Okay, I will cover them directly. After that, we will come to the another concepts, right? Seventh A group elements, very very important examples. Seventh A group elements and sixth A group elements. Sixth A group and seventh A group elements. I said to learn about sixth A and seventh A group. I said to learn about sixth A and seventh A. Okay. What are seventh A group elements? Say halogens. Fluorine, chlorine, bromine, iodine. 6A group, oxygen, sulfur, selenium, tellurium and polonium. Just now I explained one concept. See, for smaller atoms, electron affinity is more, because in smaller atoms positive charge is present on the outermost orbit. Anywhere, any point, positive charge is present, so you can add electron easily. Clear? So based on that, fluorine should have more electron affinity values. Why? Fluorine size is small. As we move down the group, size increases. Fluorine size is small, so fluorine electron affinity will be more. So what is the expected electron affinity order? Expected electron affinity order: fluorine greater than, bromine greater than, iodine. Group, within the group we are comparing. This is correct only, na? Correct or wrong? Online students, correct or wrong? Why? Tell me. Someone are giving reply. Tell me, Meenakshi, why? Subia, Meenakshi, Obed, Aishwarya, Akshara, Sanjana, Aisha. Yeah. Bhakti, are you following? Bhakti, Kritika, Surabhi, right. See the reason. Reason or correct answer. Okay. See. Correct ionization, electron affinity order. Chlorine greater than fluorine, greater than bromine, greater than iodine. Very, very, very important. What is the expected order? This is expected, right? Because fluorine size is small. But this is not correct. This is correct. One simple reason. In fluorine, in second orbit, fluorine configuration 1s2, 2s2, 2p5. In second orbit, generally second orbit radius is small. Second means not that much bigger. Yes or no? In first orbit, how many electrons can fit? 2 electrons. 1s2, first orbit. In second orbit, within the small shell, see how many electrons we have to put? 1, 2, 3, 4, 5, 6, 7 electrons. Within the small ring, if you place 7 electrons, repulsions will arise. So in fluorine, high inter-electronic repulsions are present. Very, very important. Because of high inter-electronic repulsions, it is difficult to add the electron easily for fluorine. Okay, got it? Only simple reason. Don't do any research. Why fluorine has low electron affinity value? Because of its high inter-electronic repulsions. Small size, very small size. Size should be smaller only, but very small size of second orbit. Okay, generally this reason will come in the options. Small size and high inter-electronic repulsions. Small size and high inter-electronic repulsions. Remember, directly I am writing here, all of you. fluorine has low electron affinity values than chlorine because of small size of second orbit and high interelectronic repulsions. Reason is very important. And high interelectronic repulsion. Okay, clear? In which group we can see the exceptional case? 7th A group. 7th A group and 6th A group also. These two came several times, right? Coming to the 6th A group, guess in 6th A group, see, I'll give you one simple trick. In case of 7th A, swap first two, interchange first two. Chlorine greater than fluorine, fluorine greater than bromine, bromine greater than iodine. In 6th A group, keep oxygen in last. Simple trick. In 6th A group, keep oxygen in last. So arrange these elements in the increasing or decreasing order. See, for 6th A group, order is sulfur greater than, selenium greater than, tellurium greater than, polonium greater than oxygen. Oxygen should be last. EA, electron affinity order. Very important. 6th A and 7th A group elements electron affinity orders. Clear? Sulfur size is lesser, so sulfur is having more electron affinity. Next, selenium size. Oxygen size is very small only compared to remaining, but same reason for oxygen also. You can ask one question, sir, you said if size is small, electron affinity is more, but why you placed oxygen in the last? Okay, small size only, but second orbit size is very less than the required, and high interelectronic repulsions are present. So addition of electron is little bit difficult in case of oxygen, even though its size is small. Clear? Exceptional case. So trick I'll tell you, swap first two in the 7th A, keep oxygen in last. In which? In 6th A. Clear? Online students? Okay. Tell me. That is experimental data only. Experimental. Okay. Experimental data. Okay. Now coming to the some other questions, other type of questions. Electron affinity is a which process? Exothermic process. So during addition of electron, energy is released out. So exothermic. Look at this. Electron affinity is an exothermic process. Exothermic process. I am taking one element, oxygen. I am adding one electron, O negative. How many electrons I am adding? Let us represent energy released as EA1, electron affinity 1. Okay. It is negative or positive? Negative. Why? Because energy is releasing out. I am writing some energy also coming out. While we add electron to the oxygen, oxygen is converting into O minus, plus some energy is coming out. Energy is releasing out. And why I represented as EA1, I added only one electron. So electron affinity 1 is negative, and this is which process? Very, very important. Which process this is? Exothermic process. Energy is releasing. Exothermic process. Exothermic process. No doubt. First electron affinity is which process? Exothermic process. Exothermic process. Right? Can you guess? I am taking this and adding another electron to this, which will convert it to O minus. This is called electron affinity 2. Electron affinity 2. Electron affinity 2. Then guess the sign here, negative or positive. And what about the process, exothermic or endothermic? Positive, endothermic. Very, very, very important. I'll explain clearly. First of all, I'll give you the trick. First electron affinity. When you add electron, most of the cases, 99% cases, again we have exceptional cases. When you add electron to neutral atom, that is called EA1. That should be negative exothermic, fix in your minds. When you add electron to the neutral atom, that is represented as EA1 and exothermic process. Neutral atom I am saying. But when you add electron to negatively charged ion, that is represented as EA2. Why EA2? Because already you added one electron here, yes or no? Already you added one electron, again you are adding second electron. That's why EA2, electron affinity 2. Addition of electron to negatively charged ion, always endothermic. Simple trick. Addition of electron to negatively charged ion is endothermic and it is represented as positive. We will discuss the reason also. Clear? Don't get any confusion. So generalization, second electron affinity is positive and that is endothermic. Why? Here energy is releasing, here energy is absorbing. Why? What is the reason for that? Got it? First of all, you have to remember this relation. Second electron affinity is, tell me, positive or negative?
Positive.
Positive. Endothermic or exothermic? Endothermic. Let us see the reason. One general example I will take. Right? Okay. This is one bench or compare this bench with oxygen atom. Oxygen. Bench. Okay, college bench. 3 students sat on that bench. Some electrons are present in the oxygen atom. Okay. Imagine or consider one student came late. Here one electron is going to enter. Like one student came late, he is going to sit on the bench. Already 3 students are sitting on the bench. So 4th student can adjust or not? Can adjust, right? That is 3 bench capacity only, but with congestionally 4 students can sit, right? Okay, imagine one new student sit on that bench. So total how many students are sitting now? 4 students. Similarly, we can add first electron. This is the first electron. First electron easy. You added one electron. When we add electron, oxygen will get which charge? Negative charge, right? Okay. First student, first electron addition is over. First electron addition is which process? Exothermic process. Negative sign. Now another student also came late. Will this student can sit on this bench? No. Already maximum capacity is over. Similarly, can we add another electron to this? Can we add second electron easily? We cannot add. Why? Because maximum capacity is over. Inter-electronic repulsions are present here. Before that, 3 electrons only present. Between this electron, some less repulsions are present. But after adding 1 electron, between these more repulsions are present. They only fighting for the place. Here students, 4 students are fighting for the place. Then how they allow 1/5 student? Here also 4 electrons are fighting with each other. How these 4 electrons allow to enter another electron? But the teacher decided to make to sit this student on the bench. Then what teacher has to do? Tell me. Teacher should push this student forcefully, right? In my hands, power is there or not? Energy is there or not? So I am pushing this student forcefully to sit on this bench. Means I am supplying energy or not? Similarly, these 4 electrons are not accepting this electron. So I am pushing this electron forcefully. I am giving the energy. Energy is transferring through my hands into the atom. Energy is transferring through my hands into this atom. Now I am giving energy or not? Means this atom is now getting the energy or not? That's why endothermic process. That's why endothermic. Second electron affinity is which process? Endothermic process. If you do not like to remember this concept, just remember this. Second electron affinity is positive endothermic, because addition of second electron is a little bit difficult. Okay, remember this story. First electron, this is second electron.
So always label children.
Yes. Okay, right. General concept this is. First electron affinity is positive or negative? First electron affinity is positive or negative? Negative. Exothermic or endothermic? Second electron affinity is positive and endothermic. No doubt, right? Clear? 100%. Online students, did you get this? All of you? Any doubt in this? But for some elements, sorry, inorganic means highly exceptions. Inorganic means highly exceptions. But for some elements, first electron affinity only positive. For some elements, first electron affinity only positive. Generalization, 99% cases, first electron affinity is negative, exothermic, but we have exceptional cases. The elements with stable configurations, completely filled, completely half filled, even inert gases possess first electron affinity is positive and endothermic. For some elements, first electron affinity only positive. Reason, due to stable configurations. You just remember that. Helium, neon, inert gases, dash dash dash. Helium, neon, argon, krypton, xenon and radon. Radon is radioactive, so omit it. Inert gas elements. For inert gas elements, first electron affinity only positive. Look at this. Helium plus electron gives rise to He negative. Electron affinity is positive. Endothermic. I'll upload the video. If you do not get the, again listen and you can understand. Clear? Along with inert gases, say some other elements with completely filled configurations, half filled configurations. Just a second. Nitrogen configuration 1s2 s2 2p3 stable. Say some other element. beryllium 1s2 2s2 stable. That's why ionization energy is different, exceptional order. Phosphorus 1s2 2s2 2p6 3s2 3p3. Correct. See this, ionization energy of a neutral atom is equal to minus electron affinity of its uni positive ion. Remember this relation also. Okay, uni positive ion. For example, ionization energy of sodium is equal to negative electron affinity of N nucleus. This is also important relation. Okay.